Okay, now let's take a look at a different population growth, not mold or even cutting for ballots. Let's take a look at my favorite animal, snakes. Everybody loves snakes. So garter snakes were introduced to an area 4 years ago. The population is growing exponentially. So already we know we're going to be talking about exponential growth here. The relationship between the number of snakes and the year is modeled with an exponential function. Now remember, the terms function and equation are interchangeable. They really, essentially, for our understanding right now, they mean the same thing. What you're going to do on A, numbers 1, 2, and 3, you're going to use this graph to answer those questions. Go ahead and try A, 1, 2, and 3 on your own. So pause the video, try this on your own, and then come back and see how you did. Okay, on number 1, it says find the snake population for 2, 3, and 4 years. So if we're looking at year 2, year 3, and year 4, we're looking at the graph. So right here is year 2, and so we look, okay, up here, and then we come straight over. So follow this line over to here. And we're right here. Then you have to think, well, what are my intervals? If from here to here is 100, it breaks up 1, 2, 3, 4 times. Each one of these is 25. So we have intervals of 25. Intervals of 25 sinks. That sounds like it's from a horror movie. And you notice ours lands on that first one, which is 25. So after year 2, there are 25 snakes. Then we do the same thing for year 3. Come straight over. And you're at 125 there. So there are 125 snakes. And then year 4. That's easy. Come straight over. You're at 625 snakes. That's what you're supposed to do on number 1. Now let's take a look at number 2. And it says use the pattern, and your answer is part 1, estimate the population year 1. So first of all, the pattern that we notice, you should see that to go from 25, ran out of room, to go from 25 to 125, you multiplied by 25. To go from 125 to 625, you multiplied by 25. So if we want to go backwards to year 1, we just do the inverse of multiplication, right? So, which would be division. So we would divide by 25, moving backwards, and then 25 divided by 5. So year 1, you started with 5 snakes. And then make sure you're able to explain how you got to 5 snakes as well. Pause the video if you needed to do that. And then number 3, explain how you can find the y-intercept. So then you would go backwards one more, right? Because the y-intercept would be year 0. So when we go backwards one more, you divide this number by 5, and that gives us 1 snake. So over here at our y-intercept, it looks like it's 0, but it's actually 1. And then the coordinate would be 0, 1. Right? Because when time equals 0, the population equals 1. So you could say this is year and population. All right, so that's what we're looking for. Something like that, or y equals 1 is fine too. On B, explain how to find the growth factor for the population. Well, the growth factor is this number that you're multiplying by every time. And so our growth factor is that multiplicative change, which is 25. Okay, but again, this says how to find, explain how to find. So make sure you're able to explain that it's that growth factor is that number that you're multiplying by every time. So if we wanted year 5, we would take this times 25 to figure out how many snakes then would be on year 5, which we will need to know for part C. And in fact, on part C, or part D, sorry, but on part C, it's asking for the equation, right? So if we say P is our population, and T is years. So just like I did up here, it would be P is our population, T is years, so it would be T first, because that's our x-axis, and then P for population. What information, what's the equation? So it's going to be P is equal to our growth factor to the power of time. So that would be our equation. And what information, explain what information the numbers in the equation represent. Well, there's only one number right there, and that is our growth factor. And in D, in what year is the population likely to reach 1,500? So that's where year 5 comes in, because on year 5, if you take 625 times 25, you would get 3,125, which is more than 1,500. So the answer on D is going to be between years 4 and 5. On E, Amy and Chuck were discussing whether this relationship represented in an exponential function. Who is correct? Explain why. Amy claims that it's not a function because she says if you look up here, because it's not a function if these y values repeat. So if time equals 3 years, had 2 different values, meaning there could be 125 or there could be 300, then that would be not a function. So Amy says on year 4, hey, it looks like this is a vertical line. So if we continue our line, it's just going to be vertical, meaning there are going to be parts that repeat, okay? But then over here, Chuck says, nope, that's not true. That's not it. It is a function, and it's just the scale of the graph that makes it look like it's going vertical. Right? If you think about these snakes, okay, they are growing so fast that if you don't have the right scale, it's going to look like a vertical function, because when we multiply this by 25, you're going to get a huge number. So in this case, Chuck is correct. It is a function. That population will never repeat on any given year, and so it's always going to be increasing, therefore it's a function. And that is it for 2.3, studying snake populations.